Ladies and gentlemen, we are back with another episode of our hit Solve It series, where you will get complete past paper solutions with explanations that a mere mark scheme or examiner report will not give you. It'll be a quick revision of the entire syllabus, and with a look at the latest paper formats, it will equip you with all that you need to ace your next exam. So, without further ado, let's get started.
Assalamu alaikum everyone, this is Fal Ansari and I'm here to help you conquer chemistry. It's been a long while since I made a video like this, but I'm back with the latest May-June 2023, paper 2, variant 2. We're going to solve this together because it contains some quite difficult and new questions that have not been seen before. So do stay tuned for the solutions to this paper that an examiner report or a mark scheme will not give you. So let's get started. All right, so question number 1 is talking about some substances and their melting points. So the first question is pretty basic. State the type of bonding present in magnesium and sodium chloride. So for magnesium, we know this is a metal, so it's going to be metallic bonding. And for sodium chloride, this is an ionic compound because we have a metal and a non-metal. So it's going to be ionic bonding in this compound. So part 2, explain the difference in the melting points. Now over here you can see that magnesium has a melting point of 923 Kelvin. For sodium chloride, the melting point is 1074, so it's higher. So when you have a higher melting point, that means you have stronger bonds that require more energy to break. So the simple reason for this is that we have stronger bonds in sodium chloride as compared to Mg. All right, now we need to explain the difference in the melting points of phosphorus and sulfur. Now over here you can see that sulfur is the one with the higher melting point. Now the thing is that both of these have a simple molecular structure, if you recall your concepts from period 3. So both of them will have non-polar molecules with instantaneous dipole, induced dipole forces between them. Now, the strength of these forces depends on the number of electrons in the molecule. Sulfur has more electrons, and to prove that to you, we're going to look at exactly the number of electrons. For phosphorus, we know that it exists as P4 molecules, and the proton number of phosphorus is 15, so it has 15 electrons per atom, so you have 60 electrons in total. Now, for sulfur, it exists as S8, so 8 of these atoms, each of them contains 16 electrons. So if you do the math, this turns out to be 128 electrons, if I'm not wrong. Yeah, so it has more electrons, so stronger ID forces. So let's write this down. So S8 molecules have more electrons than P4 molecules. Resulting in stronger ID forces. Now you can write that abbreviation ID, or if you remember the entire name, it's better to do that. So I'll write the entire name. So stronger instantaneous dipole, induced dipole forces. So now the next question says, define electronegativity. So electronegativity, its definition should be pretty clear to you guys. It is the ability or the power of an atom to attract bonding electrons towards itself. So these are bonding electrons in a covalent bond. So I will explain that over here. Bonding electrons in a covalent bond towards itself. So that is electronegativity. All right, explain why electronegativity increases across a period. All right, so remember, electronegativity is affected by the same three factors as ionization energy. So those factors are nuclear charge, number of shielding electrons, and the distance of the electrons from the nucleus in terms of number of shells. So now across a period, you're going to have the same number of shielding electrons and shells. So I'll write this down. Same number of electrons, shielding electrons, and electron shells. And we have an increasing nuclear charge. So that increases the nuclear attraction for the bonding electrons. So I'll write this as increasing nuclear charge. Which results in greater attraction between the nucleus and the bonding electrons. All right, so that is the complete explanation. Let's keep moving. So it says name the strongest intermolecular force that exists in NH3 molecules. And that happens to be hydrogen bonding. The reason is that you have a hydrogen atom that is bonded to one of the three most electronegative elements. We have fluorine, oxygen, and nitrogen. So if hydrogen is bonded to either of these, then you're going to have hydrogen bonding. NH3 contains nitrogen, so that's what's going to happen over here. Right, now it says we need to draw a diagram to show the hydrogen bond between two molecules of NH3. So what we will do is we have an NH3 molecule over here and another one on this side. And we know that we're going to have a lone pair on the nitrogen atom, which is partially negative. The hydrogen atoms having a lower electronegativity will have partial positive charges. So we draw all of that in over here so that we don't miss out on anything. And we have a partial negative nitrogen on the other molecule as well. So the lone pair over here on the partial negative nitrogen on one molecule will attract the partial positive hydrogen from the other molecule, and that is your hydrogen bond. It would be a good idea to label this. So let's label this over here, hydrogen bond. There we go. All right. Now it says that the melting points of ice and ammonia are shown. Obviously, ice has a higher melting point. It says we need to suggest two reasons why this difference occurs. Now, the first reason is that oxygen is more electronegative than the nitrogen, and so there's a higher electronegativity difference in O and H as compared to between N and H. And that would result in a stronger dipole, so stronger hydrogen bonds. So let's write this down. So write this as higher electronegativity of O compared to N, leading to stronger dipole on H2O compared to NH3. Now, the other reason is that H2O has two lone pairs on the oxygen atom, whereas ammonia only has one lone pair on the nitrogen. So, as a result of that, you're going to have more extensive hydrogen bonding in H2O. All right, so I'm going to write this as that each H2O forms two hydrogen bonds. Due to two lone pairs on the oxygen compared to one hydrogen bond per NH3. Now you might be wondering, I'm writing below the line. Well, that is acceptable if you are writing beneath the question and you have a bit of space. Use that to complete your answer if the lines provided are not enough. All right. Okay. Now moving on to question 2. So the first question is pretty simple. It's asking for the maximum oxidation number of these period 3 elements. They're bonded to chlorine. So for sodium, it's going to be +1. For magnesium, it's +2, +3 for aluminium, +4 for Si, +5 for phosphorus. Now the thing is that each of them has a positive oxidation state because they're less electronegative than chlorine, and the oxidation state is increasing because of the increase in the number of valence electrons. So state what determines the maximum oxidation number of the elements. Well, you just answered that question. It's the number of valence electrons. Now, part B and part C. In fact, they ask about a lot of the equations, so please, if you're studying inorganic chemistry, make sure you memorize your equations, all right? Because they could just spring them at you, all right? Without any context, they'll just ask you, okay, write the equation for this reaction. So you need to memorize that. The best way to do that is to write it down from memory and then recheck your answer. And if it is incorrect, repeat until you get the right equation. Right, so we need to first write the equation for the reaction between cold water and the chloride of silicon, right? Now, because silicon has an oxidation state of +4, chlorine, we know it's -1, so the chloride of silicon is just going to be SiCl4, all right? This reacts with water. Now remember, the chloride of silicon is covalent. It's going to react with the water and produce acidic solution. So in this situation, we get SiO2, which is a white precipitate, and we get HCl, that's your acid. So if you balance the equation, we have 4HCl to balance out the chlorine, 2H2O to balance out the hydrogen, and that's it. Now the pH of the solution, it's obviously going to be highly acidic because it's HCl, right? So I'll just write a pH of 1. Now, an excess of cold water is added to the chloride of phosphorus, all right? So in this situation, the chloride of phosphorus, you will write it according to the oxidation state because phosphorus is +5 because it has 5 valence electrons. So it's going to be PCl5, all right? So PCl5. Actually, there's also PCl3 that's there, but remember we are talking about maximum oxidation number. So that would be +3 in PCl3, but the max is +5, so we will go with that. All right, so PCl5 plus H2O. Now this is going to give us a mixture of two acids. It's going to give us HCl and it's going to give us H3PO4, that's phosphoric acid. Now to balance out the Cls, we have 5HCl over here. And to balance out the water, to balance out the hydrogen in the water, we will need 4H2O. And the rest is balanced. So just the pH of this solution, again, 1, because we have now a mixture of two strong acids. So that's what we'll go with. Now, write an equation for the reaction of chlorine with water. Now, in this situation, another equation you need to recall, chlorine, it reacts with water, and it's going to give us HCl and HClO. All right, gives us a mixture of two acids. This is actually a disproportionation reaction because if you remember, chlorine has an oxidation state of 0 because it's an element. Over here, chlorine will be -1 because it's more electronegative than the hydrogen. Over here, though, chlorine will be +1 because the oxygen is most electronegative, so its oxidation number will be -2. And for hydrogen, it will be +1, so chlorine will be +1 as well. So one chlorine atom is being reduced to -1, the other is being oxidized to +1, so that's disproportionation for you. And another disproportionation is the reaction of chlorine with hot sodium hydroxide. So remember, when we have hot sodium hydroxide, the reaction will look like this. You will have NaCl and you will have NaClO3. All right. You have 5 moles of NaCl for 1 mole of NaClO3. You'll also have some water. And to balance this out, we have 3Cl2 and we have 6 NaOH. So that gives us 3H2O. All right. Now, again, this is an oxidation state of 0 for the chlorine. 5 of these chlorine atoms are going to go down to -1, so that's reduction. And one of the chlorine atoms, one of those lucky guys, is going to go up to +5 in NaClO3. So there's an increase of 5 for one of the chlorine atoms, and there's a decrease of 1 for the other 5 chlorine atoms. So 5 times -1 is -5, and that will equal the +5, the increase in the oxidation state of that one chlorine atom. So that's how you balance an equation with disproportionation involved. All right. Now it says identify the formula of the ion present in bleach that kills bacteria. You should know this. This is the chlorate 1 ion, the ClO minus. All right. And now it describes an equation for us. We need to balance it out, write the correct formulas. So it says that NaClO reacts with hydrogen peroxide. Hydrogen peroxide is H2O2. All right. And this produces sodium chloride, NaCl, and some water, H2O, and some oxygen gas, that's going to be O2. So now we need to balance this equation. You check on both sides. We have 1 sodium, 1 chlorine, 2 hydrogens, and we have 1, 2, 3, 1, 2, 3. Yep. So it's already balanced. Okay. So yeah, that's it. And by the way, this is also a redox reaction. The oxidation state of oxygen in H2O2 is -1. It's going up to 0. All right. And so that means that 2 oxygen atoms are gaining their oxidation state by +1. All right. For chlorine, this is +1 in NaClO as we saw earlier. And NaCl is going to be -1. So that's going down by 2. So when you add the -2 to it, it gets 0. So it is balanced. All right. So yeah, it's balanced in terms of oxidation number and in terms of number of atoms of each element. All right. H2O2, by the way, reminds me of this lame joke that 2 guys walk into a bar and one of them orders H2O and the other one orders H2O2. All right. H2O, 2, T-O-O, right? The bartender, being a chemist, understood H2O2, the hydrogen peroxide. The poor second guy, well, let's just say he didn't have a good end. Anyway, moving on, we have part 3. Now this involves some molar calculations. We need to take a look at this. All right. So over here we have 10 cubic centimeters of W. This contains bleach. All right. And it has some unknown concentration of sodium chlorate 1, NaClO. It's diluted with distilled water to make a total volume of 100. And then 25 cubic centimeters of this is added to an excess of H2O2, hydrogen peroxide. And then the volume of gas, which is again oxygen over here. This is produced and it is measured under room conditions. And so we have 42 cubic centimeters of gas that had been produced from the 25 cubic centimeters of the diluted bleach solution. So we need to find the concentration of NaClO in W in gram per cubic decimeter, okay? So the first things first, we have 42 cubic centimeters of gas. We can find the moles of the gas, the oxygen. So this is 42 cubic centimeters. We can divide this by 24,000. All right. Because we know that in 1 mole of any gas under room conditions, we have 24,000 cubic centimeter volume that is occupied. Right. So once we do this, we get 0.00175 moles. Now, if I look back at the equation I did in the previous part, there's a 1-to-1 ratio between NaClO and O2. All right, so 1:1. So that means the moles of O2 that are produced will be the same as the moles of NaClO that were used. And these were the 25 cubic centimeters. All right, so remember we have 0.00175 moles in 25 cubic centimeters of the diluted solution. And the total of this diluted solution, you should remember we have is 100 cubic centimeters. Now we need to find the moles in that entire 100 cubic centimeter of the dilute solution. So once you cross multiply, you find out you need to just multiply 0.00175 by 4, and that gives us 0.007. That is the value of X. All right. Now, the 0.007 moles, which is contained in 100 cubic centimeters of the diluted solution. Now, remember that that 100 cubic centimeters is actually made up of 90 cubic centimeters. That's just water, right? That's distilled water. It contains nothing of the NaClO, and the 10 cubic centimeters is of W that does contain NaClO. So obviously the 0.007 moles have to have come from the 10 cubic centimeters of W. So now we can find the concentration, but first, remember, we have to convert to gram per cubic decimeter. Right now we have the moles. So we first find the mass of NaClO in the 0.007 moles. So we multiplied by the molar mass, so 23 for the sodium, plus 35.5 for the chlorine, plus 16 for the oxygen. So once you find all of this out, your answer should be, if I calculate this correctly, this is 0.5215 grams. And then finally, we find the concentration of NaClO. We will divide the mass in grams, 0.5215. All right, we scroll down a little. Yep. Divided by the volume, which is 10 cubic centimeters for W. Remember to convert this into cubic decimeters. All right. And then the answer turns out to be 52.15. We can round this up to 52.2. The reason is that in the question, you may have noticed that in the 10.0, 100, the 25.0, and the 42.0, you have been given 3 significant figures, all right, in your data, in all the values that you've used. So the final answer should also be to 3 significant figures. So we will write this as 52.2 grams per cubic decimeter as the final answer. All right. Okay, moving on to the organic chemistry. All right, everybody's favorite topic. Yay. All right. First part says state the reagent and conditions for step 1. Step 1 basically converts chloroethane, CH3CH2Cl into X. Now what you're doing is replacing the chlorine with this CN. All right, this is the nitrile functional group. All right, and to convert a halogenoalkane into a nitrile, you need ethanolic KCN. So potassium cyanide is dissolved in ethanol, and you need some heat in order for this reaction to take place. Now it says give the systematic name of X. Now this is a nitrile with 3 carbon atoms, including the one in the functional group. So this is going to be propane nitrile. All right. Now it says identify the type of reaction that occurs when dilute acid is added to X in step 2. So in step 2, when you add dilute acid, the nitrile is converted into a carboxylic acid group. Now this happens when you hydrolyze a nitrile. Okay, so this is going to be hydrolysis, specifically acid hydrolysis, because you're using dilute acid for this purpose, and it gives you a carboxylic acid. All right. Now in step 3, Y and a gas are produced. We need to construct an equation. Now this carboxylic acid is reacting with a metal. Remember, whenever an acid and a metal react, they give you a salt and hydrogen gas. So the gas over here is hydrogen. So we have 2 marks for this equation rather than the usual 1. And the reason for this is 1 mark is for identifying the gas, which is hydrogen. And the second mark is for ensuring the rest of the equation is correct. So we will have CH3, CH2, COOH. This reacts with calcium. Now the salt that you will get is CH3, CH2, COO. Now this ion over here, the propanoate ion, has a -1 charge. So there's going to be 2 of them to balance out the +2 charge on calcium. Plus you have H2 gas. To balance this out, you need 2 moles of propanoic acid on the left-hand side. Right. Now, propanoic acid can also be formed from propan-1-ol and potassium dichromate 6. State the conditions required. Okay. So if I am oxidizing propan-1-ol, which is a primary alcohol, all right, remember that primary alcohols, they first are oxidized to give you an aldehyde, but if you want to just produce an aldehyde, you need to distill the product. But if you want to continue all the way to carboxylic acid, you need to heat under reflux. All right? So the condition over here will be heat under reflux. Not just heat, has to be under reflux so that the complete oxidation takes place. And you also require H+, or you could just write acid. The reason is that potassium dichromate 6 and, by the way, potassium manganate 7 do not work so well if you do not acidify them. So they need to be acidified oxidizing agents, and of course with heat under reflux. Now, it says we need to complete the number of sigma bonds and pi bonds present in a molecule of X. All right, X again was propane nitrile. So I'll just draw a rough structure over here. So we have CH3, CH2, C triple bond N. That's the nitrile group. Now over here between the carbon and the hydrogen atoms and between the carbon atoms themselves, we have single bonds, so they're all sigma. So sigma bonds, we have 1, 2, 3, 4, 5, 6, 7. And within this triple bond, we have 1 sigma bond as well. So that's 8. And in a triple bond, remember, we will have 1 sigma and 2 pi bonds. So the 2 pi bonds come from the triple bond in the nitrile functional group. All right. Okay, now, next question. We have to find the delta H for the reaction given above. Over here, we have the hydration of ethene to give us ethanol. All right. Now for this one, the first things first, we will calculate the bond breaking energy. I'll just write this as delta HBB, bond breaking. Always look at the reactants first and the bonds broken within them. All right. Now for C2H4, we know that it contains 1 carbon-carbon double bond and 4 carbon-hydrogen single bonds. So that's going to be 610 for C double bond C. And we have carbon-hydrogen single bonds. That's 4 times 410. plus we have for the H2O, remember that's just HOH, so you have two OH single bonds, so that's going to be 2 times 460, and this gives us 3170 kilojoules per mole. Now for the bond formation energy, BF, bond formation, you look at the product side, all right? So for C2H5OH, I know this is CH3, CH2OH, all right? So over here, I can see that I have 1, 2, 3, 4, 5 carbon-hydrogen single bonds. So that's going to be 5 times 410. Plus we have the carbon-carbon single bond, that is 350. So we write that down. Plus we have the carbon-oxygen single bond over here. So that's going to be 360. Plus we have the OH at the very end, so that's going to be 460. So this all turns out to be 3220 kilojoules per mole. So now you know what to do. Delta HR for this reaction is just going to be bond breaking energy, that's 3170, minus the bond formation, that's 3220. And that's going to give us minus 50 as the final answer, and that is in kilojoules per mole, obviously. All right. Now, one little shortcut that could have been used over here is you may notice that we have 4 carbon-hydrogen single bonds on the reactant side. So I'll write this over here. We have 4 carbon-hydrogen single bonds over here. And on the product side, we have 5 of them. So the difference is that 1 carbon-hydrogen single bond is being made. So even if I got rid of the 4 times 410 on the bond breaking energy, and instead of writing 5 times 410, I would have just written 1 times 410, all right? If I just wrote this as 1 and I got rid of all of this together, that would have given me different values for bond breaking and bond formation energies, but I would have gotten the same answer at the end. It would have been a neat little shortcut, but because I am a man of principles, so I am going to write the full form method over here so that you know that this is the actual method to use. And we're not actually, discounting any bonds, for any random reason, right? It's just that they appear on both sides. So that is why we have split the difference. Anyway, so now it says that reaction 1 reaches equilibrium at constant temperature and pressure. We need to find the effect of increasing the pressure on the amount of ethanol that is produced. So if you look back up at the equation, over here we have 2 moles of gas on the reactant side, and on the product side we only have 1 mole of gas. So if I increase the pressure, that will favor the reaction producing less moles of gas so that the pressure goes back down according to Le Chatelier's principle. So this will increase the amount of ethanol that is being made. So I'll write this down. So effect of increasing the pressure, the amount of ethanol in the equilibrium mixture will increase. And the explanation is that we have fewer moles of gas on the right hand side, the RHS, so the forward reaction is favored. All right. Okay, so moving on. Now this equation, this question over here that shows this weird looking mechanism that I've never seen before, is actually the reason why I'm doing this paper, okay? So you need to pay very close attention to this. It's actually given a different mechanism for the hydration of ethene as opposed to the one that is in the syllabus. And the reason is that it is involving the phosphoric acid catalyst, okay? So it says over here, describe the behavior of H3PO4 in step 1. All right, in step 1, what happens is that an electron pair from the pi bond of CH2CH2 is being transferred over to this H, and the bond pair between the H and the O is going to the O, so it gets a negative charge. All right, and the hydrogen is bonded to the ethene, and it makes a carbocation over here. Now the thing is that the phosphoric acid, we know it's an acid, and we know the definition of an acid is a proton donor. And that's exactly what it's doing over here. It's donating one of its protons to ethene. So we will say that it behaves as an acid. PO4 behaves as an acid as it donates H plus to ethene, C2H4. All right. Now it says identify the species that behaves as an electrophile in step 2. Okay, so in step 2 over here, you can see that we have the ethyl cation, all right, the carbocation from step 1. It is gaining a pair of electrons, the lone pair of this oxygen over here, because it's itself positively charged, it's deficient in electrons. So what we're going to say is that the C2H5 plus behaves as an electrophile since it gains an electron pair from the O atom in H2O. And we know that electrophiles, they gain electron pairs because they are quite literally electron lovers, right? They are attracted to lone pairs of electrons because they themselves are electron deficient. All right. Now over here, we need to complete the mechanism for step 3, okay? So this was produced at the end of step 2, and this is what we have from step 1. Now you can see over here that this particular anion is being converted back into H3PO4. All right. So that means that the catalyst is being regenerated, right? Now the way this will happen is when it gains a hydrogen ion. It donated its H plus in the first step, it needs to get that back, all right? So this lone pair on the negative oxygen, all right? And what happens is that this is going to be transferred to the H over here, obviously because it needs to form a bond with the H, all right? H plus can only be accepted with the help of a lone pair on the negative atom. Now over here, to balance out this positive charge, the bond pair between the hydrogen and the oxygen needs to be broken. So the electrons will go to the oxygen from this bond pair so that it is completely neutralized. And this guy over here will be leaving as H plus, that the O minus in this anion will be only too happy to accept. So this is basically how you complete this question. Now describe how a catalyst affects a reaction. Okay, blah, blah, blah. This is very simple. You've studied this in IGCSE as well. So we know that a catalyst speeds up a reaction. Now how does it do that? It does that by providing an alternate reaction pathway with lower activation energy. Speeds up a reaction by providing an alternate reaction pathway with a lower activation energy. So basically that means that more molecules will have enough energy to collide successfully with each other and form the products. Now it says use figure 4.1 and 4.2 to justify why H3PO4 is described as a catalyst. Now the thing is that one thing about catalyst we know is that it is not used up, all right? It does take part in the reaction, but it will be generated or reformed at the end, okay? So over here, we know that in step one, H3PO4 is being used up. It's being converted into this anion over here, the H2PO4 minus. But in step 3, it is being converted back. So we will say that H3PO4 is being regenerated or reformed in step 3 after being consumed in step 1. All right. Now, it says propene also reacts with steam and a mixture of organic products is produced. Explain why propan-2-ol is produced at the higher yield. All right, so if you look at propene, this is CH2, double bond, CH3. Now, if this were to react with steam, now the hydrogen could either go to the CH2 or the CH. If it goes to the CH2, then you're going to get CH3, single bond. Now the CH will bond to the OH over here, and we have CH3. Now it says the propan-2-ol, which is what we've just drawn, is produced at the higher yield. The reason is that before the OH bonds, all right, we have a carbocation, and this carbocation is actually secondary, all right? And we have two methyl groups with a positive inductive effect on the positive carbon atom, and that stabilizes the positive charge, which means that more of it will be formed. And then the positive carbon atom is going to attract the lone pair on the OH minus, and that's what's going to bond it to the OH. Now the other possibility is if the hydrogen were to bond to the CH instead. So we would have a CH2 with a positive charge, single bond CH2, CH3. Now we know that this type of carbocation is primary. It only has one alkyl group, so a reduced positive inductive effect. So the positive charge will not be that stable. And so it will not be formed as much. All right. So I'm going to write this as that propan-2-ol is formed from a more stable carbocation due to a positive carbon atom bonded to more alkyl groups leading to a greater positive inductive effect or the electron donating effect. All right. So basically, the way I explain this one to my students is that, the positive carbon atom is in need of help. It's in need of electrons. All right. It's going through a hard time. So to stabilize his situation electronically, the methyl groups that have more electrons help him out by donating electrons to him. All right. So, you could relate this to a poor guy going through hard financial times. All right. Okay. Moving on. So you talk about ethene. All right. We have the structure that we drew earlier. So now we know that in the sigma bond, we have hybrid orbitals involved. The carbon atom over here is bonded to 1, 2, 3 other atoms. It has no lone pair, so this is going to be sp2 hybridization. So we have two sp2 orbitals that are involved in the sigma bond. Remember that the pi bond is formed between two unhybridized p orbitals. Now, how the orbitals overlap over here, in the sp2, they're going to be overlapping end-on or head-on, or you could say direct overlap. And for the pi bond, we know that's going to be side-on overlap of the unhybridized p orbitals in the carbon atoms. All right, next question. More organic chemistry? Yes, please. So we have structural isomerism that needs to be described. Okay, so we know that this is pretty regulation definition. All right, we have basically organic compounds with the same molecular formula. But what's the difference? They're two different organic compounds because they have different structural formulas. So that's the description of structural isomerism. All right, this is the easiest question that you could get from isomerism. All right, so the guys who were taking this paper were lucky to get a break with this question, especially looking at the questions before that were a little more difficult than usual. All right, so in part B, we are talking about two structural isomers with the molecular formula C5H10O. Some information has been given about these two. Now it says we need to name the functional group present in both of them, right? So the first reagent, 2,4-dinitrophenylhydrazine, shows an orange precipitate in both A and B. All right. So that means that both of them contain the carbonyl group, which is the C double bond O. All right. Now it says we need to draw the structures of A and B in the boxes. All right. For A, it says that a silver mirror appears with Tollens reagent. So that must mean that A is an aldehyde with 5 carbon atoms. So we will draw it like this. We have CH3, CH2, 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 CHO. All right, that's 1, 2, 3, 4, 5 carbon atoms. Now, when it comes to compound B, there's no reaction with Tollens reagent, so it must be a ketone. A, we know this was an aldehyde because of the positive result with Tollens reagent, but with B, it has to be a ketone. Now, the thing is that we have two possible options when it comes to the ketone, all right? What I mean is that we have CH3, CO, CH2, CH2, CH3. This could be pentan 2-one, all right, with the C double bond O on the second carbon atom. Or we could have pentan 3-one, where the C double bond O is right in the middle of the structure. Now, how do we tell which one is going to be the correct option? Now, the thing is, it says over here with alkaline aqueous iodine, we have no reaction. Now, remember that when it comes to carbonyl compounds, if it contains CH3C double bond O, then it must give a yellow precipitate with alkaline aqueous iodine. In this situation, the first option does contain this group, but because we have no reaction with B, this is the incorrect structure, and this is going to be what we're going to go with. All right. Now, one important thing is that over here it says draw the structures. Now, it's up to you if you want a structural formula, displayed formula, skeletal formula, whatever you want. All right. If they specifically said structural formula, that this is what you would do and nothing else. If it was skeletal formula or displayed formula, you would go for that specific formula only. All right. Okay, moving on. Now it says that C is a structural isomer of A and B. All right, so it has the same molecular formula as per our definition earlier. This is going to be C5H10O still. Now it says that It is straight chained and it has two functional groups, and it shows only one type of stereoisomerism, all right? Now it says over here that it does not show a reaction with 2,4-dinitrophenylhydrazine, so it does not contain C double bond O, that's for sure. All right. Says bromine turns orange to colorless. All right, so that means we have a C double bond C somewhere. And alkaline aqueous iodide gives us the yellow precipitate that we're looking for. But remember, because we don't have C double bond O, so instead of CH3CO that we were looking at earlier, the other group that gives us a yellow precipitate with alkaline aqueous iodide is CH3CHOH. All right. So now we have two functional groups, the OH and the C double bond C. So we need to draw structure with this. So we'll start with CH3CHOH. Now we have 3 carbon atoms remaining. Now where do we place the double bond? We have 2 options going forward. So the first option is that we go for CH double bond CH3. All right. Now in this situation, you can see that if we talk about stereoisomerism, there's 2 types. There is geometrical, all right, and there's optical. Now for the optical isomerism, that is definitely there in option C, in this particular compound C, because this carbon atom is a chiral center. It is bonded to 1, 2, 3, 4 different groups. All right. So we want to make sure that there's no geometrical isomerism anywhere, right? There's this chiral center only, that's it. Now the problem is that if we look at this double bond, we have the carbon atoms in a double bond. Each of them is bonded to 2 different groups. The first one is bonded to H at the CH3CHOH group, and the other carbon atom is bonded to an H and a CH3. So this will show cis-trans isomerism or geometrical isomerism. So we only need to stick to one type of stereoisomerism. So this double bond will not do. So we will place it between the second to the last and the last carbon atom. So the better way to write this would be CH2. And then after this, we have CH double bond CH2. So that is the complete structure, and it only has one type of isomerism, which is optical. All right. And that's, by the way, the next question. It says, name the type of stereoisomerism, and that is going to be optical in compound C. All right, now we have D that is reacting in the presence of sulfuric acid to form E and water. Now, the functional group present in E, we have C double bond O. Now, you might think that this is a ketone, but wait, it is bonded on the other side with an oxygen. So that completes the functional group, which is an ester. Now, identify the type of reaction that occurs when D reacts to form E. Remember that esters are formed when a carboxylic acid and alcohol group come together. They make an ester, and water is the byproduct, small molecule that's eliminated. So we will write this as a condensation reaction. Now it says we need to draw the structure of D. Now the thing is, we're going to be working backwards. We're going to break the C single bond O over here. All right. And the oxygen is going to be bonded to an H to make the alcohol group. The C double bond O will be bonded to an OH to make the carboxylic acid. So I'm going to redraw this over here. So the O is bonded to an H to make the alcohol. We have a CH3 over here, and then CH2, CH2, and then we have a C double bond O that will be further bonded to an OH to make the carboxylic acid. All right, and that is basically D. It contains both groups, and when they come together, you get a cyclic ester, which is E. Now finally, we have an infrared spectrum for E, and we have some wave numbers and the associated bonds. It says that we need to find 2 differences in the absorptions above 1500 per centimeter for the infrared spectra of D and E. All right, so we need to find the differences for D compared to E. Now, if I look back at the structures for D and E, I will notice that in D, I have the OH single bond over here and over here, which will result in absorptions for the OH bond. And in the case of E, the C double bond O is part of an ester group, whereas in D, the C double bond O is part of a carboxylic acid group. So even though it's the same bond, the wave numbers will vary a little. All right, so we'll write that down. So for D, we have an absorption at approximately 2500 to 3000 for OH in the carboxylic acid group for D. All right. You can also write that we have another absorption at 3200 to 3600 for the OH bond in the alcohol group in D. All right, that's another acceptable difference. But I'll just stick to the C double bond O. All right, so we will say that there's an absorption at now for D, the C double bond O is part of a carboxylic acid group. So the range will be over here. For E, because the C double bond O is part of an ester group, the range of wave numbers is slightly higher. All right, so I'm going to write 1670 to 1740 for the C double bond O in the carboxylic acid group for D. All right, so these are two acceptable differences. I could write about the OH single bond in the alcohol group for D, or I could write about the fact that the C double bond O in E, the ester, is going to be at a slightly higher range of wave numbers from 1710 to 1750. That's all good. All right, and yep, that's about it. About the May-June 2023, paper 2, variant 2, we are done. All right, and in good time as well. You get an hour and 15 minutes, and we're done within an hour. So that's awesome. All right, so if you want me to do more past papers, if you want me to do a specific past paper, do leave your comments below. And if you like this video, do subscribe to the channel. And I'll see you in the next video.